Currently in industry, there are two ways to test the properties of materials: destructive testing and non-destructive testing. In aviation, an example of destructive testing is when a jet engine is tested. It is broken down in order to determine mechanical properties such as strength, toughness, and hardness to see at which point your material eventually gives up and cracks. Each layer of the engine has stress applied and is scanned and measured. After the test is performed, the engine cannot be used anymore. This is a waste of resources. In non-destructive testing, the component is tested and it is still usable after the test. An example of this is an MRI machine. It performs tests on people without having to take them apart. If a non-destructive testing can be applied to jet engines and materials in general without having to destroy them to test them, the resources would be saved. However, there are many different types of destructive testing and non-destructive testing.
Currently, Professor David Giles and his research team of graduate students at ISU are researching a way to accomplish this using magnetism. Similar to how the magnetic properties on a magnet change with temperature, so do the properties change with stress. When a material is magnetized, the properties change if stress is applied. The research group is attempting to calibrate this correlation so stress testing parts can be accomplished by magnetic instruments.
We were fortunate enough to be able to walk through the process of magnetically testing a material in person in a lab at Iowa State and get a general overview of how the testing works. The most important component is a very sensitive sensor that has a current-carrying coil inside of it. It is then mounted into a stress-inducing device and hooked up to an alternating current output source. The reason alternating current is being used here is because the atoms within the material have magnetic dipoles that are pointed in random directions. We're seeking to manipulate the direction of these atoms' polarity. The current goes through the coil in the sensor and forms a magnetic field. As the name alternating current suggests, the direction of the current changes 100 times per second, which also changes the direction of the magnetic field. When a metal has stress applied to it, it creates dislocations or small points in the metal that are no longer flexible, whether temporary or permanent. This is what the sensor is testing for and how you can tell if the structure has been compromised near a surface. Finally, we turned on the displacement reader and zeroed it out to make sure everything was ready to go and all the testing devices were communicating with each other. After getting some readings, we needed to make sure the sensor was firmly against the specimen so we didn't get any careless bad readings. We made sure everything was on track and started manipulating the tension. After adding some stress to the specimen, we took a measurement of the voltage. The students and faculty working on this project gain a variety of information, and a lot of their research is finding new applications to the information gained from these readings. We were told some of the most important information for us to pay attention to was derived from the equation root mean squared. Since the sensor cannot take an infinite amount of readings and the polarity is always shifted, it finds the absolute values of the voltage compared to the stress, since half would be negative from the alternating current, and it finds the root mean squared of the value. This is a great way to take information from discrete or discontinuous readings. A notable thing the team at ISU discovered is that 1 over the voltage is proportionate to the peak stress value. After our first reading, we took one more and it verified an increase in the RMS with an increase in the stress in a predicted way from the known material.
In this video, we highlighted magnetic non-destructive evaluation, but there are many other kinds. Some are even as easy as painting an object, while others include radiography, ultrasonic, and thermography. All of these have their strengths and weaknesses, and their own place in industry. Another interesting application of non-destructive evaluation is the off-site method by combining NDE technology with robots. There are some robots that have been specifically designed to climb walls and test objects that are hard to get to. There are even some designed to climb wind turbines that are in the sea. Without these robots, people have to go out to them, dismantle the turbine, bring the blades back to test them, and then also take them back to sea. Other automated testers inspect pipelines that are hundreds of kilometers in length while also changing diameter. making these robots a necessity. These pipelines are buried underground, so without these robots, we would have no way of knowing of a failure until it occurred. Preemptive measures like this are the forefront of preventing disasters on large-scale structures. Non-destructive evaluation has come a long way, but the more research that is put into new methods, more injuries, deaths, and business losses will be prevented. Even with the advances of non-destructive testing, most companies still prefer destructive testing. NDE, unfortunately, is not yet as effective as destructive testing and testing complete failures, but it is only a matter of time and research, with creative ways of using physics.